Today we're going to be talking about compressor oil. More specifically, I had a dream in the middle of the night that I cooked compressor oil inside the basic compressors, and we said, you know what, let's make it a reality. I've never done this before, and neither has Ty, our special guest here, and so we thought, you know, what the heck happens when compressors get really hot? And we can kind of imagine the things that take place inside compressors, but sometimes it's just better to just to do it, right?
Well, for me, it's curiosity. What happens? What if? And we'd actually talked about this months ago, and we had answers, and I said what I know, you said what you know, but we still had questions, and we reached out to everybody else we know, and we had some really good feedback, but there was still some unknowns. And so, man, what a better way than use that curiosity and try and figure it out. And so that's what we did.
Yeah, so we went out and we bought an induction cooktop plate. I've got a bunch of compressor bodies that are kind of laying around here at the base. So I don't know really anything better to cook compressor oil in than an actual compressor. And so we're going to take these compressor plates, we're going to clean them inside with RX11 flush to make sure they're nice and clean to not contaminate our results. Then we're going to take different types of oil. We've got mineral, we've got POE 32, and we've got PVE 32. Cook each individual one for at least 10 minutes at their flash point, 346 degrees, give or take, around that 340 degree, to see what happens to that actual oil when you apply extreme heat to them.
And also, we want to make sure that nobody tries this at home. When you're cooking or heating oil up, it becomes very dangerous. We have all the safety gear and the PPE and the fire extinguisher and the glasses and the gloves and the fire department nearby and the EMT and all the stuff. Everything you can imagine, it's done behind the scenes outside the camera. So don't do this at home.
Yeah, don't try this at home. But again, this is that factor of, hey, you've got an idea, you're curious about it. Why not, instead of asking a bunch of questions and then not getting any answers that we're looking for, maybe not all the answers, we got some, but not all of them. Let's find out for ourselves what happens when you cook compressor oil. And this should be simulating exactly what happens inside of a compressor that has a discharge temperature around 215, 235, 245, right? That's exactly what we're trying to simulate here so that we can talk about a lot of things. Contamination, oil breakdown, lubricity, a word which I'd like to say a lot, and see what we find.
And this is the POE 32, PVE 32. This does not include the higher temperatures such as POE 32B or the 46 or the PVE 68 or something like that. So it doesn't include the specific high temperature refrigerant oils, gesture basins that we use most commonly today.
Yeah, that's it. So stay tuned and let's get into it.
Good cooking.
We're at what, 175 degrees? You can actually start to see some smoke there. At 200, 225. Some serious smoking now. 250, 275. Starting to get some more rapid movement. We are at 300 degrees, 340, and we kind of hit our smoke point a little bit under. It's not as much discoloration as I thought they'd be at 350 degrees, but it does look like there's some though. Doesn't look as clear as it was before. We're at 347, and this is the official smoke point. So it started clear. Yeah. Now the question is...
It was crystal clear.
Crystal clear. And we even have some left over, obviously, so we could just do a comparison side by side. But that, to me, looks yellow.
It does look yellow.
So the whole point of this is to find out what happens to oil when we add high temperatures to them, especially within compressors, in the compression process.
I see contamination inside of there. Is that from the oil, pieces of the oil carbonizing?
It might be.
Or was that in there before? It looked like it was pretty clear before.
Oh no, we only had a few specks.
And there's a lot in there.
I wonder if we turn it back on again and cook it a second time.
Let's turn it on, let's cook it some more.
And so the amount of time that has transpired between brand new oil to hitting 340, 345 degrees is maybe 5 minutes?
Yeah,
maybe
not
10?
very long.
Not very long. It's a very short period of time. We're talking a very, very short period of time.
Oh, and let's also talk about where you would see the high temperature. Right? What's going to cause the compressor, the system, having these high temperatures?
Yeah, no, so insufficient refrigerant flowing through the compressor, keeping the compressor cool. A lack of oil lubricating not only the scroll plates but the upper bearings, the lower bearings, the things that you see like in your average compressor at the top and the bottom of both of these bases here, that eventually leads to the additional friction, right, added between metal on metal.
I am pretty sure that we have a lot more carbon in there than we had at the beginning.
Yeah.
That's
well, and this is such a short period of time. What's the average time would you think a compressor short on gas would last? I mean, or even the state that it would stay in for an extended period of time. I mean, it could be
even if we think of how long it would be before the customer, they have a leak or they have some situation, how long is it not cooling very well? How long are they running really high super before they ever even call us?
Yes.
Before they even say, hey, this thing's not cooling, you're talking about a good amount of runtime. So a system is going to be running low in gas for a while.
Several days.
So this is happening for a long time. And then you got to figure too, since it's not cycling off because it's not reaching set point. So now it's like this for, a significant amount of time. And then by the time we get the call scheduled and we get out there to the customer's house, there's a significant amount of heat built up on that compressor.
Or let's even talk about the amount of compressors that get to the extreme state of overheating, right? And then they actually discharge that hot gas onto that device that we have inside there, that safety device that's inside the scroll compressors that are designed to actually disconnect one of the windings and turn the compressor off. And then you get that cycling where it cools down enough to restart the process again, and then it cools down enough to restart the process again, and then cuts off, and then on and off and on. It could be weeks.
Let's cool this off. Let's compare what this oil looks like in a clear glass with how it was renewed.
Brand new, fresh, mineral.
So let's compare. Let's do that. How are we going to cool this off so we can test this?
Air, let the air naturally.
Well, if it was before 1987, we could just take some refrigerant, turn it upside down, and spray it, and that would a lot of liquid. But we do not do that because number one, it's illegal, and number two, ozone depletion. So what else are we going to use? We can use ice, right?
Yeah, we could.
We could actually take ice. We could set that into ice. The reason that ice works is because it's 144 BTUs to change ice from a solid to a liquid. 144 BTUs. So ice is an option. We could also put it into a freezer. We could just let it cool off naturally with temperature. There's lots of ways we could do this.
Refrigerator. Yeah. We have a case over here, so we could just toss it in the case.
We do have a case. And if we do that, we got to make sure there's no other food in the case. And our case has no other food in there.
Yes.
If you were to put anything hot in a refrigerator, you've heard the whole thing about, hey, we should, if you cool food down faster, it's better, less bacteria builds up. And that's true. But also, if you put something hot in your refrigerator, it does cool it down faster, which is great. But also, that heat goes to everything else in the refrigerator and cause that temperature to rise, which means that other food is also more susceptible to the bacteria and growth. This is a big topic that came up recently because they were talking about doing tests, but they only did the test with what they were testing. They didn't do tests with the whole environment of what else is in that refrigerator.
It's funny you say that because when you think about the amount of heat that we've added to this oil, it's not just the oil, it's the entire compressor housing body here. And so there's a specific amount of heat that we've added to it. And taking that specific amount of heat and setting it inside of another structure like the refrigerator or the case, we're now adding that to that environment.
That's right.
And if the environment isn't designed to handle the total amount of BTUs that we've added to this piece of metal, it doesn't just disappear.
That's
right? It exchanges inside the refrigerator. Now we could overwhelm the refrigerator, right?
Yes.
And then what you're talking about is taking something that's designed to be at 37 degrees, 40 degrees in an ice cold refrigerator and overwhelming it with something it's not designed for, and then getting it above a specific threshold of, let's say, 60 degrees, where other foods will actually start to decay faster, right? Where the bacteria growth starts to increase over time. And so, yes, you could essentially cause food to go bad from putting hot things like out of your oven, some baked spaghetti, why not, and toss it in your refrigerator, not knowing that you should probably let it cool down to room temperature first before adding it to that refrigerator.
So right now you're pouring in fresh oil directly out of the container. So this is exactly what it looked like when we poured it into here. And being that it's a brand new clear beaker, you can see exactly what that looks like. Ooh,
kind of has a yellow tint to it already.
Just a slight bit, but it's quite clear. There is a very slight yellowish tint, but it is a clear choice. It's easy to see through. It's interesting, even pouring it in, you see the bubbles from the air as you poured it in. And wow, here you can really tell the difference.
I mean, it's night and day.
It is.
It is night and day difference. On one hand, you've got clear, right? You can see the contamination under the table. But on the other hand, it's yellow. And this is just mineral oil. So we're testing a lot of different oils today. We're doing mineral oil with ISO 32 mineral oil. We're doing PVE oil, and we are also doing POE oil. We're gonna do ISO 38 and also 60. Was it 64? 32 and 68. There we go. POE. And just because we can, we'll also do some vacuum pump oil too, because if we're here doing science, you might as well do all the science and not just a little bit. But yeah, man, that is crazy. When you put them side by side like that, look at it. And I say it's crazy, but you and I both know exactly what's taking place here. On the left-hand side is the oil that we just cooked live, and on the other side here is the actual fresh, clear mineral oil directly from the jug, no contamination, from the factory, nice and dry. The difference between the two.
You can also see bits of carbon floating around in here as well. And there is a significant amount of carbon inside of the original here.
What is Ty exactly talking about? Ooh, let's look at it. Oh, there they are.
Yep, that's carbon. So what's happening, the oil is literally having a chemical reaction as it gets too hot, and it's turning into carbon flakes. It's literally cooking, and now we have contamination flowing through the system. Now, the longer we do that, the more carbon we end up with having, and what's going to happen to that carbon?
Oh, it's going to get all over the place. It's going to clog expansion valves.
Yes.
It's going to clog strainers.
It's going to clog strainers, yes.
You know what? Let's suck up a piece of carbon.
How about you also have your capillary tube, or your what you call distribution tubes for your reversing valves. Those little bitty pilot tubes. That's what I'm looking for, pilot tubes. Those are going to get clogged up. Oh, nice. Look at there. You got a nice piece right there.
Yeah. See if I can get it over there without making a mess.
There it is. Perfect. Look at that big piece of carbon.
Look at that flake.
It's so flaky.
Just light, airy. So where did this occur? This occurred at the direct source of heat under the actual plate at the base of the compressor.
So we got this down. We've seen with mineral oil, we saw the carbonation, we saw that discoloration compared to its original. So what oil are we going to test next?
Let's do POE.
Okay, so now we're going to use polyester oil, POE oil, and let's see what it does.
No, so you've got here, looks like smoking around the base here. Looks like maybe paint discoloration as well as some smoking maybe from the paint.
Could also be from the POE oil that soaked into the paint. When we were filling it up, we dripped some. We cleaned it off really good, but it can soak into that oil or soak into the paint. And that's why we want to also make sure we keep the oil off the roofs. That POE oil, it's this type of solvent. It can actually, clean. So on these, especially these vinyl roofs that we work with, that can actually dissolve or break down that roofing. So making sure that if we're doing compressor changes on the roof, we want to make sure that we protect that roof. So putting down mats, rags, extra piece of roll of vinyl in there, something to help protect that roof from not just puncturing, taking the heavy compressor off, but the oil itself. And it's cool to see the separation here.
Yeah. Starting to show up on the camera. You can see the different wavelengths. It's almost the comparison that I use a lot is when you look across a hot road,
yes,
like asphalt, and you can see the differences in
reflection of the light.
Yeah. Looks like it's almost like there's water on the road when there's not actually water on the road. It's just you're picking up what you see is heat, right? Definitely cooking for sure. I'm showing 150 over here on both sides, even temperature. The temperature of the oil, it hit 200 degrees, and then we started getting some random smoking right there at the top. And now here, we just started cooking it, and we're getting smoking around the base on the outside. The opposite effect.
But it's also important to note when you talk about the mineral oil, it doesn't immediately, it's not hygroscopic, it's not trying to pull the moisture out of the air. On this one, even though it's the same size can, once we open this can, it's starting to pull the moisture out of the air. Just opening this up, looking inside and closing it back, it's already let air in, and the moisture from the air is going to immediately start absorbing into that oil.
What's interesting is we've got like bubbles.
Little bubbles.
That are still present.
So as we pour this into this container, the force of the oil going in, it's also bringing with it air. So we're literally mixing air and the moisture together, and also moisture from the air. So when we're pulling a vacuum, we pull those contaminants out of the oil, which is why it takes longer to pull a vacuum with the oil. So we do have some of those contaminants that you wouldn't typically have. As soon as we open this, we let the contaminants in. Yep. So we won't be able to use this container in the field. It's done. Even though we only use that little bit, there's no practical use for this anymore, because It's just a complete waste.
So that goes out to those technicians who have had oil containers on their van where they've only used half of it. The understanding is that once you crack a POE container, it's done for. So either whether you use it all then or use it later, you can't use it later. Now people are going to say, well, what if they put it in a deep vacuum?
Sure.
Or triple evacuate?
If you can find a way to store it and keep it in a deep vacuum, but if you try to put this can in a deep vacuum, it's going to implode from the air pressure, that static pressure on the outside.
And that's a video you've only done, what, like 7 times now?
A few times. Yeah, I've done it a few times.
But also, too, to that point, they're going to say, well, what if you just put it in the system and dehydrate it? The point that they're missing here.
Yes.
The point they're missing here is what's taking place inside that oil inside the can while it's not under a vacuum. Why it's sitting on your shelf in your van, jostling around, waiting to spill over and soak all your tools in oil like it normally does. There's something that's taking place. You want to talk about that?
That is a chemical reaction. The oil itself, when this is hygroscopic, it's not just pulling in the moisture, it's actually having a chemical reaction to itself. It can literally start turning into an acid right there, and we can't pull that back out. Once it's having that chemical reaction, we can't pull it back out. Now, if we have the mineral oil, we can definitely dehydrate it. We can pull a vacuum and pull that moisture back out, but once we have that chemical reaction here, it's there. It's there forever. The only way we're going to get it back out is removing the acid with filter dryers and removing any of the moisture that's in there with actual filter dryers, which cost more than the oil itself in our container.
Yeah.
And notice these containers are also in metal. The mineral oil, we could buy that in plastic containers, no problem, but this is metal. Now the question is, why do we use metal instead of plastic? Specific reason is because it's so hygroscopic, it's potentially possible to pull moisture through the air, through the pores in the plastic.
Yeah,
where in the metal, it won't. Yeah, here we go. Plastic's cheaper. It's a lot cheaper to buy the plastic. More easier to work with.
This is mineral.
But that's mineral oil.
Yeah.
It's not hygroscopic, but this one is so hygroscopic it can literally pull the moisture potentially through the plastic pores, which is amazing. Like, that's how sensitive it is. So if you have this, we don't want to leave it open. Like, once we open this for this little experiment, it's done. That's it. Unless I guess we got some really heavy duty metal container, poured it in, and then immediately pull the vacuum, immediately after pull it through, which is just, it's just ridiculous, right? I mean,
we may use it to melt some plastics and styrofoam later, but that's about it.
We have some other experiments we're going to do with this, but as far as using it in a refrigeration system, it's done. So we actually would put a big X on top of this to know that, hey, this has been opened before, and I actually have a marker right here.
Which again, to the point of that also, you'll notice that in the top of the mineral oil, it comes with a tiny little seal film that you see when you normally open like a bottle of ketchup, right? Or syrup, right? With this, it's an actual metal punch-out tin that says cut this out. And once you completely break that seal, as if you're opening a can. But yeah, to that point though, I mean, you know, there's a reason there's a tin on the top of that as opposed to the actual mineral oil itself. But I know a lot of guys, it's great to keep things on your van, right?
Yeah, for sure.
I'm the kind of guy that wants to be prepared for every situation and scenario, but a lot of times we don't understand the consequences of doing something like keeping a jar or a container of POE oil on the truck after it's already been opened. And again, we want to utilize our tools to the best of our ability. We don't want to waste. We don't want to throw things away that shouldn't be thrown away, but sometimes this is one of those things where you have to throw it away because that's best practice.
And my question to the manufacturers out there, why are you guys putting these in smaller metal containers?
Yeah.
So that we don't have to waste as much? Because, you know, a lot of us aren't big on the environmental side of things, but you got to think that's oil that goes to waste, it's going to go into recycling. But if we use smaller containers, then hey, we could here we go. Here's another. So we know that you can do it. I'm looking at it right here. I'm going to cover
PVE.
I'm going to cover the brand name of this, but it's PVE oil. So I know you can do this.
Yeah.
I'm seeing it right here. Why don't we put the POE oils in containers like this? Right? It's not that cut. We need more. We buy more containers. I don't know if anybody's ever used a full gallon of oil, even on. Well, I guess there's some scenarios, but it's very rare. Like. Anyways, that's my rule.
It's got to be something with containers. Maybe they get a discount on containers that size. But you'll notice here we stopped smoking, so we've boiled off all the contaminants or oil around the base of the outside of the compressor. We're at 250 degrees. This one's showing a little bit higher than that, about 260. Notice how when we hit 225 with the mineral, it started smoking.
It did.
And here we are at 250, and we have zero smoke. If anything, you don't see any more refraction or reflection in the light with this. Now you can see some things floating around inside of the actual oil that kind of look brownish, but yet I have yet to see, I mean, so looking at this, so standing here next to you, this doesn't look hot.
It doesn't.
It's like glass. It's settled, it's calm, it's cool, it's collective. Not knowing that if I dropped water in this, we'd have a giant explosion.
Oh, yeah. It would be bad. It'd be bad. But it's a great point. Like, I wasn't expecting the mineral oil to be smoking way before we got to its flash point. It was smoking. And then because of that experience, I expected this to do that. And it did not. So it's interesting to see just right here doing these experiments of what's really happening is, you know, it's not smoking. And that's also because this is a synthetic oil. It's manufactured. It's not a natural oil like the mineral oil is. So I don't know if it has to do specifically with that, or if maybe that's one of the reasons that they used the POE oil, because it has that lower temperature. It's a great question. And that's what here, we're playing Discover. Now, we haven't practiced this or tried this out. This is pure curiosity as we go.
Yeah, I'm not a scientist. I have no special scientific degrees that tell me that I'm some kind of expert at anything. We're literally just two guys trying to figure out and get to the bottom of this. What really happens when you cook compressor oil? You know, this is basically a cooking show about compressor oil.
That's right.
It's still mind-boggling that we've hit 250. So I think now, from the sounds of it, it's maintaining. The induction cooktop is now maintaining. It thinks that it has hit 300 degrees, which I'm not saying it hasn't. We have a lot more metal here at the base than we had on the other compressor. So what I'm going to do now is I'm going to turn this to...
What are we at temperature-wise here on the thermometers?
We're at 260.
Right.
So we're at a lower temperature than what it thinks it's at. And so
crank it up!
We're going to turn it up to 350 and see what we can get it to do.
Remember, 325 to stay alive, 6 inches from the discharge, because at 6 inches from the discharge, at 225, it's actually going to be closer to 300 and something inside the compressor itself.
Yeah, there's a great tech tip at HVACschool.com where we talk about, exactly that. Just because you sense the temperature at the discharge outlet does not mean that there isn't higher temperatures within the core of the compressor. We've got a lot of layers to peel back from that internal components all the way till you get to the outside, and so this is of the the same thing. And so now here we go. We've got the lines back again. Yep.
You can see the convection happen. You can see the warmer fluid moving to the cooler. Oh, I'm starting to see flakes floating around.
Yeah, I saw that too.
I couldn't see any before. You saw some, and I couldn't see it, but now I see several.
So these nuts that we see here in the bottom of the compressor, these are actually designed to house magnets right here. So these came actually from the compressor themselves. They're designed to catch more metal particles through the operation of the system. Copper shavings, as you can kind of see here. There's a good amount of copper shavings on there. Metal paste. This is from scroll plates. That is designed to actually stick to the nut that's here and not just wrangle around inside the system. And so we've removed those, but unfortunately there is a little bit of copper shavings you can see on one of the nuts. Right here in this picture too as well. There's a few copper shavings that we missed. We tried to make this as clean as possible by cleaning them with RX11 Flush and wiping them down to make sure we don't skew our readings or change the color of the oil with something other byproduct that might be present inside the base of the compressor. So these are pre-cleaned. However, you can't get them 100% clean with a pressure washer, but then we have to deal with the rust that takes place
and the moisture and yes.
Yeah. Which kind of negates the whole purpose of why we're doing this in the first place.
And it's like I say, this isn't full-on scientific experiments. These are two guys that's done HVAC their whole lives, and we're just curious about the science of things. And this really has science started out. Hey, let's do this experiment. Let's do that experiment. Oh, we found a flaw in it. Let's just redo the test and make it better.
Yeah.
And so this is our starting point.
Oh yeah, now we're starting to cook.
Well, I see flakes circling around. I think it's slightly changing color. Before you could really tell it turning yellow, but now I'm just now starting to see it.
Yeah, we're at 260 on that one. We're getting close to it.
There's a good sized flake right there that's formed.
We're getting to 300 now.
Look at this piece right over here, right next to that nut. See that one? That's
wasn't there before.
Pretty sure that wasn't there before.
What's interesting too is how much the temperature influences the fluid movement that we see that's taking place here.
Yeah.
It's not sitting still.
No.
Right. As we add heat to it, the molecules inside of this entire apparatus here are just starting to move more and more and more. And naturally now we're actually starting to see that flow. And yeah, you can see the brown, right? There's one there, there's one there, there's one there. Okay, so it sounds like it's maintaining again, and we are at about 305, 304. This one is showing about 275.
What did we get up to last time?
So last time we got up to about 346.
All right, let's hit it. Let's go there.
Oh, and so can't go from 300 to any other step except for 350, but yet when I click the button, we go to 390 from
Let's
350.
see what happens. And of course, we have different thicknesses in our compressor here versus the other one. It was a little thinner metal.
Yeah.
And this is why we're measuring the temperature directly in the oil itself with not just one, but 2 thermometers, so we get a good idea what's really happening.
Yeah, we always want to be biased in the point to where we're taking these measurements in a lot of different places so that we make sure that, one, we're being safe and we're following all best practices, but two, we really want to get down to the root science of getting this to that smoke point, or right below the smoke point where the oil actually starts to turn to a smoke, and see what happens in the actual makeup of that oil. I'm starting to see a lot more brown flakes than I thought was there before.
Yeah, I'm pretty sure that that's an increasing number of little flakes floating around in there. And it looks to me like it's not nearly as dominant as it was in that mineral, but it looks like we're getting a little bit more color turning.
Discoloration, yeah.
Discoloration, there we go. Discoloration. Thank you for that.
All right, so we are at 325. This one's getting a little closer to 300. So we're getting up there for sure in temperature. And again, notice the huge difference, right?
Yeah, we can start to smell it now.
Yeah, you can actually see the smoke coming off the actual oil.
It doesn't smell pleasant at all. The mineral oil smelled much better than this.
Not that we recommend you inhale any smoke.
Do not inhale any smoke. Well, we have invisible respirators on for protection. I got some invisible gloves on, but we do have our safety glasses on, and we have a fire extinguisher next to us. We have a fire blanket over here. We got another fire extinguisher over there, and there's one over there. And I'm assuming they are in date. Is that correct?
Yep.
Okay, good. They are in date. And we also have a fire sprinkler system, but we don't want the fire department to come. We do have the doors open. We got fans running. We got ventilation in here. You know, we're trying to be as less dangerous as possible. We do not recommend anybody doing this at home.
We are trained experts as far as this video is concerned.
As far as this video is concerned.
All right, so we've hit 350.
350.
I'm gonna go ahead and hit it. It's interesting to see the differences between the two types of oil. Now, although they serve the same purpose of lubricating compressors, lubricating scroll plates, lubricating reciprocating compressors, we still fall into the same category of these are completely different oils. Their actual molecular makeup. And their anti-wear properties too. I don't know, it still kind of looks clear. What's interesting is the different viscosities of it. Now, obviously,
it is a lot thinner being warm.
It is. It's almost like a motor oil, and then this feels more like a water at this temperature. I'm not seeing a ton of change.
It actually looks the same. Interesting that, so just from a not pure science perspective, just from an observation standpoint, it looks like POE oil will handle the heat better than mineral oil.
Yeah, it looks like it.
I was not expecting that. Now, we don't have the full oil analysis and everything to check through, but we can, as far as color alone.
No smoking only took place at a high temperature of 345. No foaming action taking place. There
was contaminants in here in this one. Looks like some carbonization, but it was nothing like it was with the mineral oil.
A little bit more, you good? Temperature is close to, I don't know if you here, sit on the metal table for a second until it cools down. We're at 275.
Still pretty hot, 275. That's hotter than boiling. Water boiling. Water would be boiling at a higher temperature. Now, at a lower temperature.
I would love to say that they're not different colors.
They are. This one is slightly different, but nothing as prominent as it was with the other one.
With the mineral, yeah. No.
It's definitely a little bit of a tint change in there.
Side by side, I have yellow tinted glasses here that I'm wearing on my face. But you're right. Okay, so there is a noticeable difference between the colors. Your sample that has no contamination, no moisture, well, some moisture now, but fresh out of the can from the factory, cleaned, ready to go, is very clear. There is no color tint to it at all. There's some microbubbles in it, but the other sample is like a brownish yellow tint to it. Nowhere close to what we saw with the mineral oil, but there is a difference in the color. And so if there is a difference in the color, it makes you also wonder, you know, what is actually taking place? What has taken place to cause that?
What we're going to do next is we'll show you, this is the one that's hot. And it's really hard to show. I guess it's not going to show up like I wanted, but it's flaking over here. It's very watery like. The viscosity of it's really low. And then we compare it to our other sample, it's really, really thick.
Yeah, it's like olive oil almost.
All right, let's see if it shows up in the camera or not. I'm going to put the rod in. You'll see it dripping off.
Sounds like water to me.
Okay, we're going to clean the rod. Now we'll try it with this one. It's just not showing up on the camera as well, but it does. Notice how it's holding more on.
Yeah.
It's sticking to the rod more on the cooler sample.
That's the difference of the temperatures.
Yep, and the viscosity. So this just being hot, it has nothing to do with it being cooked. It's just as oil heats up, the viscosity becomes thinner. And when oil is cooler, the viscosity is a lot thicker. This is also important when we have off-cycle migration. So when that oil is very dense and thick, it'll hold more of that refrigerant. So as we drop the pressure, that oil boils out, that thicker oil will make bubbles, and as it's making bubbles, that bubble level is rising, and it literally drops the oil level down. When you have thinner oil, it's not as likely for that to happen, especially it's warmer, so it's less likely to have the migration, which is a great point of a crankcase heater. But if we get it too hot, we lose lubricity.
You know, what's interesting too is, you know, our control sample has just been basically taking it out of the can, putting it inside the actual compressor base here, and then heating it. And as I'm noticing here over time, the longer it sits here in the base of this compressor, it does seem like it's starting to turn a browner color than normal than what we started with in the first place. And so I'm wondering also how long from exposure to high temperature afterwards, right, the running in a system over and over and over again, how quickly it starts to change and cause that issue between, you know, the lack of lubrication from changing what it was from the factory and what it's supposed to be for that anti-wear properties to what it is now, and how it also might cause those temperatures to spike as well. So not as dramatic as I thought it would be.
Yeah, I'm honestly, I'm disappointed and impressed at the same time. I'm disappointed because I thought it was going to be dramatic, but I'm impressed because, hey, it held up.
Yeah.
Wait, I used to love mineral oil. It was my oil of choice. And seeing the test and see how it handled the temperature better, I'm impressed. I was not expecting that. What are we down to temperature-wise here?
I think we're both surprised. So we're at 200, 225.
I wonder what the temperature is of this. It's still warm, but it's pretty warm.
Gonna have to wait for that to cool off. So
we'll cool it off. We'll put it in our petri dish, and we'll see if there's a difference.
Do some PVE oil now, huh? A little bit of bubbling on the top. That definitely was a lot more bubbling on the POE oil as opposed to the PVE oil. You clearly see the bubbles at the top. Now they're kind of like colliding with the probe itself. But as we started to heat this up, those bubbles are starting to pop. You can see the little glimmers of light there. The lines that are starting to take place. It's no different than when light reflects off the top of a pool surface.
A few reasons for this too with the bubbles. As we poured it in, it's just Bernoulli's principle really, is the force that water is coming in, the velocity, it's actually pulling with it air, which is how aerators work in an aquarium. You're causing, it's not just putting the bubbles into the water, it's the movement of those bubbles that are coming through. So we're putting air in just simply by pouring it in. As we heat this up, those molecules move faster. The temperature of the oil becomes thinner or more viscous. The viscosity becomes thinner, but also the air molecules are heating up. As the air heats up, they become less dense or lighter, so they're more likely to bubble up and out. Same thing happens to the refrigerant, which is why we're heating up the crankcase, so the refrigerant will turn into a vapor and boil out of that oil.
And what's interesting now too is also our compressor bottom is not even touching the hot plate. It's actually only sitting on the three legs around the outside. So it will be interesting to see how the heat is evenly applied on this one as opposed to the other one that we had.
And it's interesting, it looks like fracture, look at glass, like you took a hammer to glass and it just cracked it, or ice. Actually, it looks more like ice. If you were to like take a hammer on ice and fracture the ice where there's liquid underneath, that's what it looks like.
Like crystals.
Yeah, from my point of view, but it's unlike ice. It's moving. Those lines and fractures are moving.
What's also interesting too is that we're not just heating the oil itself directly, we're actually heating it through the base of the entire metal. So everything around the structure of this is getting hot. So any kind of contaminants around the outside of this are naturally going to smoke over time, which is what we're seeing now. Is that the smoke isn't coming from the oil that you're seeing on the camera, it's actually smoke from oil and other things around the outside of the compressor base.
Also note that we used 3 different compressor bases specifically so we didn't cross-contaminate between our samples.
Yep.
Now, I'm sure there's some oil impregnated in that metal that we couldn't get originally, but we cleaned it really well. We used RX11 to clean it. But we used 3 different ones. That way, all the sample from this one, we didn't get any cross-contamination or any of the other particles from one to another. What are we at temperature-wise? I can't see it from my angle.
You are at close to 200 degrees.
That is fast.
Also, it seems like I put a little bit more oil than we did in the other ones just for the volume's sake, but I really would love to see what happens at those higher temperatures when we have a higher volume. I'm starting to see some actual particles floating around, but we are only at 225. So this is the temperature they say to stay alive.
225, stay alive. Now that's the discharge temperature, 6 inches from the discharge, which means it's closer to 300 and something inside the compressor itself.
Oh, you can see a lot of the little brown.
Yeah.
Well, and so now here we are at 275, getting close to 300, and we are actually starting to get some vaporization of the oil.
Which we didn't have with the POE oil, and I was not expecting this
wasn't either, yeah.
to be doing that. And this is why, assumptions versus, hey, let's check and see, it's important because...
We could have easily looked at some white papers and done some Googling and come up with an answer, but I mean, it's so much more fun to do this.
It's not just the smoke or the butter, this is literally coming from the inside also. So it's the oil itself that we see that's vaporizing.
Yeah,
and that's
that blow around the base, you get a good idea what's coming out of the top.
It's quite interesting.
And we're at 300 now. What do you got on your side?
We're at 300 on my side.
Okay. Consistent temperatures. We're getting a little bit above that. Yep. 315. No exacerbated changes that I've seen yet. I mean, there's a lot of particles floating around. The fluid is moving a lot.
It's cool how the oil has changed too, like how it, and all of them did that. As it gets to a certain point, instead of it looking like the ice over water, it starts turning into lines, and it looks like you're looking across a hot road where you see those waves. That's kind of what it looks like when I look down into the oil.
Well, and the difference here too is when we look at, let's say, light reflected off of the top of a pool surface, right? It's one surface that's constantly moving and changing, right. And that light reflects on a wall or a ceiling somewhere, and it's very crisp. It's got a lot of lines to it. This one here, as hot as it is, it's so rapidly moving, like boiling water does. That the lines are just all over the place in all directions, and now we're definitely getting some smoke. We're at 330.
Yes, about the same right over here. Yep.
Okay, so we're right at the edge where we're supposed to be, and as you can hear, it's actually the induction cooktop is maintaining, thinking that it's at 350. I think we're getting a little bit hotter than
I don't see any discoloration.
I don't either.
I don't see
I am very
any
surprised.
Flakes in there. I think the one that was, I just don't see. I think if anything, it may be just what was around that nut. The other two had way more flaking than this one did. The first one for sure. It's interesting to think that the mineral oil didn't handle the temperature nearly as well. I was not expecting that. Like, I used to love mineral oil as my favorite oil, and now I'm kind of like,
We've earned it.
I have to come back off of that now.
You're reassessing all of your life choices.
I am.
At this point, yeah.
And I knew that as far as thermodynamics go, there's already numbers that proven that POE oil has better heat transfer properties than the mineral oil, which is one of the reasons they chose it. So the mineral oil will actually coat, or all the oils will coat the inside of the tubing of the evaporator coil, and that slows the heat transfer from the air we're trying to cool to the refrigerant. So POE oil actually transferred heat at a better rate, which is one of the reasons they chose it. And I don't know that PVE oil was around or an option at that time, but I haven't seen the numbers on PVE oil, how fast it transfers heat, but I imagine that math is out there, the science is out there available. But what I want to point out here, back to our main topic, is I do see a lot more flakes floating around than we did earlier. I can now see them moving consistently over, so we are getting...
And you can see it here too, it looks like a...
Yep.
looks like algae, right? That's the best way to
does,
describe
yeah.
it, right? Well, a glass of water left on a Florida sidewalk,
Right.
give it 6 hours. It looks something like this. And we are maintaining at a little under 350. How's yours looking?
I'm just right under 350 myself.
Okay, so we're right at the smoke point for this oil. Specifically, or around there. You know, my reading for this was fairly light. So, but again, the consistency that I found there was after a specific temperature, usually around 350, they start to actually could potentially smoke or catch fire. So now clearly we can see the smoking. So it's all right. You ready to cool it down? And,
Let's cool it down.
Take a look at what we actually got. So I saw maybe 1-2 particles floating around, and now
There's a lot.
It looks like a bunch of sea monkeys.
See, I've never seen a sea monkey. I'm just going to take your word for that.
This is again. It looks like algae. I mean, you can see it. You've got large brown particles now floating through. This is everywhere now. So again, we've cooked this probably for I don't know, probably close to 10 minutes. 10 to 15 minutes at 340 degrees ish. And here we are. We've landed now at what looks like a bunch of contamination that we've created. Not from cross-contamination within the compressor, but actually by cooking the oil and changing its molecular makeup. Maybe I'm saying that. Rachel Kaiser will correct me later. But this is extremely interesting. I was hoping for more yellow.
You were hoping for yellow. I was
hoping for yellow. So now I'm really curious to see what the other experiments hold when it comes to that
How
color
long
change.
did we cook the mineral oil for? Was it 5 minutes?
I think it's about 5-10. Yeah.
So we've actually cooked this one for longer than we did the mineral oil, and we still don't have that yellow tinge like we did. That's quite interesting.
It is.
Now, to me, it still looks just as clear. It'll be interesting to see what it looks like when we put it into our sample.
Yeah, and also on top of that too, the Petri dish where we can actually put a backlit underneath it to light it up. All right, well, we'll let this cool down and we'll take a look at it. It's gonna smoke for a little.
It's taking a while. It's taking longer to cool down. We're still at 3.
You know what? So here's another interesting thing to talk about while we're here. How much and how well compressor bodies hold heat.
Yeah.
So we've turned this off now. And we're actually kind of maintaining temperature, if you will. We've come down, I'm at closer to probably 305 from the 340, and it is naturally going to fall over time, but you add compressor windings,
yes.
You add a rotor,
yep.
You add scroll plates, we're
heavy.
adding mass to the compressor, and
exactly
the more
right.
mass we have, the more surface area we have that's going to hold that temperature. And
that's right.
So you get a lot of guys out there who are trying to cool down compressors that have overheated, and they'll get it with a water hose, and they'll soak the outside, and they'll take their hand and they'll put it on the outside of the compressor, and they'll be like, okay, it's good to go.
Cool.
Let's turn it on.
Inside.
And they wait 2 minutes after they've turned off the water, and the compressor returns to the original temperature
yes.
it was when they got there. And that's again because you're not getting the water to the center. What's happening is you're actually exchanging the heat on the outside,
right.
but then it's having to equalize with the temperature in the center of the compressor.
That's right.
And so a lot of times, just because the outside is cooled down doesn't mean that the center of the actual compressor is also cool. And this just shows that, because again, our compressor body here, even though it's a fraction of what it actually is in the field, still holding heat. So it all settled on the bottom there, and now that I've kind of mixed it up, you can kind of see the floating particles that we've created through actually cooking this oil. It kind of distilled towards the bottom and floated naturally to the base, and so I'm going to let it settle back down again because I want to scoop that part up and put it into the actual beaker. So something to remember too when we're talking about lubricating internal components of the compressor over time. We are talking about a system that is designed to, especially for this type, this is for a VRV scroll compressor, it's designed to use pressure differential to push down on the actual oil to get it up to the center sump. And so there are magnets at the base to help absorb some of that metal particles that might pop in or pop out, but you have to remember the type of breakdown that we're talking about, that's carbonized oil, actually, is not something that would be normally magnetized, and so it's not going to stick to the magnet. So it gets kind of swirled around, if you will, and then sucked up the center, then goes into the hot bearings, it goes into the scroll plate, it interacts with the refrigerant, which is again a part that we're missing from this experiment is the refrigerant aspect, right? What part does the refrigerant play in overheated compressor oil? Now that's not something we can exactly
And we're also
test.
missing out the pressure side, being in a pressure controlled environment with no moisture, no oxygen. There's several aspects that we are missing from this.
So it is an impartial test. We're merely just applying temperature, high temperature, to compressor oil and finding out what are the repercussions of just high temperature itself. No outside interactions, no pour vacuums, obviously maybe a little bit of moisture, but no direct actual water. And then, no electrical failures. Ooh, look, it's in the bottom.
Oh, it is a difference. You can now see the difference in the oil.
Oh wow.
Yeah, there is a significant difference there.
That.
Way more than I expected.
Oh yeah. Oh wow. Okay. All right. Okay. Hold on. Watch this. Okay. Can you see the big particles?
Yes.
Okay. And let's enhance.
Oh, look at all the little ones. Wow, I didn't even see those.
I didn't either. Look at that. That is insane. So how do we know that we've created carbon in the oil by cooking it? Well, sure, we could say by the big flakes, but when you actually get down and use this type of magnification, you can see more than just that. And oh my gosh, look, you can actually see, look at this. You can see yellow dots. Let's stir it up a little bit. Oh, unless the yellow is from the paper from below, but oh, it looks like it might be. But either way, the amount of contamination that you can see moving around inside of the dish, it's pretty severe. Here's the thing, right? People will say, okay, well, how severe is it, right? How bad could it really be? And when it comes down to it, it's like, well, listen, if there isn't any in it from the factory when they manufacture the oil and it's perfectly clean, if there is something in it, it doesn't matter what level it's at contamination-wise, it's not a good thing. And this is exactly what this shows here. Any level of contamination is a bad thing.
I agree.
And now again, okay, this test, again, we're not scientists, there's a lot of impartial judgment here with stuff that we're doing here, but however, the important thing to remember is we let the oil sit to cool down, and then we actually went around the base of the compressor where a lot of the stuff that was created in the oil settled, and we scooped exactly that stuff up to put it in this so that we can see it. So I'm curious to see if you still have some in there after I sucked up the worst of it, to see if it's still in there. So now we get to the best part, right?
Yes.
Instead of looking at it under this scope. So this is a document camera. It's not a microscope, not a digital microscope. Behind me, I have a digital microscope that we're actually going to take this oil and we're going to put it in Petri dishes from what we've cooked and what we haven't cooked, and we're going to look at it on the big TV behind us and actually highlight some of the things that we've seen and kind of go from there. So we have our three samples here. We have our mineral straight out of the container, mineral cooked. We have POE, POE cooked, PVE, PVE cooked. Yes, this is a cooking show in case you're wondering. And now what we're going to do is we're going to put it on our digital microscope over here in the backhand right side, which is also on the TV right behind Ty. That's going to show us exactly what it looks like in specific conditions. So if you just grab the Petri dish. So this is our mineral oil, right? Now the yellow dots is not the oil. I thought the same thing. It's actually the paper.
Oh, wow. I didn't know that.
Isn't that crazy? So what we can do is we can take our stick here and we can swirl it around and move our oil. This is fresh from the factory, right? Don't get dizzy. Not a lot to see here. Okay, so clear oil, yellow spots again are not the oil. Let's switch it out for the actual contaminated, cooked version of it, which is a lot different of a color. Remember, we cooked these for about 5 to 10 minutes. Obviously, you should cook your compressor oil to the level of doneness that you like. Just kidding, don't do that. What I'm going to do now is highlight the contamination that we created,
wow.
And then I'm going to adjust the microscope here to pick up right there.
Wow.
There.
Look at the sharp edges that we have. That's impressive.
Yeah, and so we can actually wish this one around a little bit. You can kind of see the other particles that are floating around in that oil.
Oh, yeah. And again, the yellow is the paper, but these particles here you see floating around.
Yep.
Wow, there's a bunch of little bitty ones.
Yep.
Quite interesting.
Yep, so we've created our own contamination in the mineral oil from cooking it, and now you can see some of the distillation that's kind of floating around on the surface there. So, all right, so that's mineral oil cooked. Don't recommend it. Also, the yellow tint, yellowish tint. also not good either. So now let's move over to the POE oil.
Polyolester oil right here.
Non-cooked. Right, again, the yellow
This is our
spot.
control.
Now you can see we got a little bit of contamination in there, probably from either our hands or, in that process.
It's not moving, so I think it's on the
maybe it's at the
on the
bottom of
dish then.
itself. So okay, clear oil.
Yeah, these pieces are moving. I think that's air bubble.
Yep.
Yep.
Okay, so that's our control sample. Not a lot to see there. Again, we don't expect it to be. Very clear. This is the oil that we found did not smoke until we got to close to 300 degrees. And now let's look at it after we've cooked it. And what we're going to find here is some contamination. So you can see, if I whisk this around, there's a little spot over there, yeah? There's some spots in that oil, yeah, right there. If I move this dish, actually I see one right over there. Move this dish around. Looks like a particle. There it is. It's right there on the edge.
Oh, right there.
There it is.
Now whisk it. Oh, well, you don't want to whisk it too much. You'll lose it.
No, but there you go. So this was that brown contamination that we were talking about in the POE oil. Remember, we only cooked this for 10 minutes, and your average compressor is probably cooking for weeks, if not months, before we get to this point. So you can take this, multiply it by 100, and not only in quantity but also probably size. And again, this is not present in our control sample, and that's how we know the difference between the two. Now you could say, what about cross-contamination in the compressor? We've cleaned these compressors thoroughly, not saying we can't have any. We might have some, but this brown particle that you see here is actually pretty conducive with actually what we found in the PVE oil. So again, contamination from cooking. You can see it present in the oil. Look at these little tiny particles here. Now it may not be a lot to you, but remember, as long as there's some, then that means we know it's not a good idea. What happens over time, quantity, so yeah. Anything I missed there?
No, it's really good. And I do want to clarify too, in your regular systems, they turn it as pretty standard RPM, but when you get to VRF systems,
we're overclocking the compressors. We're running close to 7,500 RPM. We're able to overclock it in certain situations and scenarios. For scenarios where you have low ambient conditions outside and you've got that high compression ratio, especially when we get into vapor injected compressors. There's a lot of other mitigating factors to those compressors. And so again, Mitsubishi VRF uses POE. So
when these particles are moving that fast, it's almost like sandblasting at some point.
Yeah, and not only that, but also, this is a small level of contamination compared to what we might see in an actual compressor. And remember, this is a controlled test, so we're missing windings, we're missing scroll plates, we're missing all the things that you would normally have in a compressor when you cook it at this temperature. And so this is just what happens to the oil without any other external factors inside of that actual compressor. All right, and last but not least, our favorite.
Oh, not last yet, but the last oils yet. PVE, polyvinyl oil.
Yes.
Oh wow, look at that.
Well, so the yellow again is the dots
the yellow
of the paper.
Is the paper.
But yep, if we go a little bit above the paper, there's not a lot. So this is the clean sample. So we shouldn't find anything. We're watching you manufacturers. If we find something, we'll send it back. Ah, there it is. No, I'm just kidding. That little black. Again.
Let's stir it. See if that's actually in the oil or if it's on the bottom of the dish. Oh yeah, it's in the oil. It's moving around, so there must be some cross-contamination from the eyedropper or something, maybe, or maybe just some contamination in oil. I don't know.
Well, you have to remember that there's certain factors that they probably say are acceptable levels. So maybe this fits in that acceptable level.
Interesting. Wasn't expecting to see that.
They didn't expect us to look at it under a microscope, did they? They just expected us to put it in the compressor and call it a day. Little do they know about us. So the difference in discoloration, and that one's interesting. We must have put it in too hot. Look at the cloudiness at the bottom.
Yeah, I think it warped the plastic.
But look at the contamination.
Oh my gosh.
Right?
Oh wow, that's way, you can't even see that in the...
So look, I'm going to keep the paper still, and let's move it around.
Oh wow.
Look at the level of contamination. Now,
that's a lot.
We cooked this sample more than you would normally. We cook the other ones, but again, these small particles that you can see, these are little flecks of contamination that are not present in the original oil that we cooked into the oil. Now, we didn't add anything except for heat. And so what happens to compressor oil when you add heat? Well, again, it breaks down the oil to the point where you get contamination like this. So the science is really clear here. high temperatures above a certain level causes the oil to break down, and it creates contamination within the oil that then looks like this. So what are we trying to avoid? High temperatures in compressors. What happens when you get high temperatures in compressors? Well, then we recommend going and doing a compressor cleanup procedure. Filter dryers, cleaning the system, not adding acid neutralizers to take care of something like this. Filtration, right? Filtration. Don't try to take the easy way out of this and go buy a product off the shelf that says, we'll clean up your compressors and lickety split, because it's not likely. We have to filter that oil and clean it out. And again, we cook these for such a short amount of time, which is the crazy part to me. Yeah. I expect 1 or 2, or maybe have to sit here for all day cooking it.
Well, right? I'm just looking at this thinking, hey, it looks clean. It looks good. There's nothing in there. And then we put it under here, and it's like, wow, it's quite shocking to seeing it. I was like, we're not going to see anything. And then that was
And again,
not expecting
you've
that.
never done this. I've never done this. However, we just thought, hey, why not? I've never done it before. Let's find out what actually happens. And this is actually it's really cool science.
So things I weren't expecting. I was not expecting the PE oil to start smoking so early on. I was not expecting that.
The mineral.
The mineral oil. I was not expecting the mineral oil to start smoking as early as it did. That completely caught me off guard.
Yep.
I was not expecting it to turn so yellow, and I was not expecting it to have so much carbon or that big of a carbon. So that caught me off guard. I wasn't expecting the POE oil to get as high as it was.
Yeah.
And I wasn't expecting such a low amount of carbon in there. I thought it would do something similar to the POE. So that caught me off guard. And then the PVE oil, I wasn't expecting to see.
Wow. Look at this.
The contamination. Oh, wow, here, that's a, wow.
So here's the thing with this microscope. We're looking at now a jar of PVE oil, and because the PVE oil has depth to it, right, the microscope has the ability to focus in at different levels and different dimensions. And so here at the surface of the oil, we have large flecks, right? And as we go deeper into the oil with the magnification, right, clarity, you can see the particles change in positions until we get to the bottom.
Oh, wow, look at all that.
At the bottom is where we find the most contamination. Now remember, I let the oil settle over time, and this is why I wanted to show this, because this really shows the level of contamination. You're like, okay, well, maybe.
Wow, that's impressive.
Maybe they're faking all of this, and so let's just. Yeah, don't get dizzy. But look at it.
Would you look at that? Just look at it.
And again, you can't fake this evidence, right? This is the oil cooked over time. We're looking through the different layers of that oil all the way down to the bottom, where guess what? It sits. What happens to the oil in a compressor? It sits to the bottom, right? That's where the oil sump is.
Yep.
That's why this is so dangerous, because that's where all of this stuff is going to go when the compressor turns off. And then guess what? What gets sucked up first? This.
Yes. Yep.
This is what gets sucked up.
And all the bearings and all the moving parts and all the compressor moving parts. And then this will relax like sandpaper, right? So all those moving parts, you're grinding this in between it.
Expansion valves, capillary tubes.
On top of that, expansion valves.
Strainers, So those of you out there who are looking at this and saying, you know what, the last compressor I changed out, the contractor swore they used nitrogen when they brazed. They made the contamination you found in the system could all be contributed to high temperatures within the compressor. High discharge temperatures, lack of lubrication, compressor overheat, oil overheat, compounded over time, which leads to these particles getting caught somewhere in a strainer.
Yep.
Because eventually, remember, these particles, as small as they are, as they build in quantity, they start to collide. It's no different than how planets are formed, right? It's cosmic dust floating around that collides with each other. and they run into each other and they stick. And then they run into more things and they stick, and they run into more things and they stick, and it's this combination over time that creates these giant clumps that clog strainers, that clog orifices, that clog expansion valves. It's the total contamination.
Transmission tubes, for example, in the pilot tubes and a reversing valve, those little bitty tubes, and then a pilot valve has that little bitty valve and a reversing valve, miniature valve, that all these can clog up in there, and it's just the list goes on and on and on.
Crazy.
Oil ports, oil movement ports.
I'm not gonna lie, I've had a lot of fun just doing this experiment, just to see what we can actually cook up.
And what's neat about this, we recorded all the steps all the way through, so maybe awkward in the final, but there was no preparation for this. This is truly our first time seeing it, as it is your first time seeing it.
Literally half of the things you see here on this table were ordered ordered on Amazon and showed up today, halfway through filming this. So yeah, again, this is just us trying to get down to the bare bone basic science of what happens when you do this. And for our instance, what happens when a compressor internal temperature reaches 320 degrees, 340 degrees, this is what happens. And what do we see on a compressor for this? Well, that's a 245 degree discharge line. That's a 245 degree refrigerant temperature. That equates to compressor internal temperature being close to 320, 340 on some instances where this can take place. So.
And we try to keep cross-contamination down as much as possible. We use 3 different ones of these. We use different beakers. We clean the beakers in between. By we, I mean Roman Broca-meter. Yes, here's our 3 different samples here. Our 3 different ones. So we tried as much as we could to keep them all separate. We used Petri dishes. We covered the top. There's always some contamination on the very bottom of at least one of those. But it's not a science laboratory. It's not completely a clean room.
We use 3 different compressor bases. We clean 3 different compressor bases. But again,
the results are still. You can see that. Hey, that's actually what's happening here. Straight up.
Well, and I'm even still blown away that the mineral oil changed colors so quickly.
Yeah, I was shocked. I thought one of the other ones would have changed color first because we
PBE
see
for sure. PBE for sure.
And it didn't. It's very little tint change in that. A little bit. You can't see it in the Petri dishes as much as you can. Now, yeah, that did not come from our testing today. That was actually
this is from a failed compressor out in the field, and a lot of guys are going to say, well, the temperature and this is leak dye. And the whole start of this process was, is this actually leak dye, or is the color that we see here a byproduct of overheating windings? And that's the real question that we're trying to answer here, of working through these experiments to get to the bottom of why is this oil the color that it is, and is it leak dye? Is there another contributing factor? What causes this? Because a lot of guys are seeing this in the field, and I don't have the answers for them, so let's figure it out.
So the next thing we need to do is do some more tests of possibly running them for a longer time at the heat. So say run them in an hour and see if how big the changes are.
Yep.
Try them with contamination. I don't know if we have time to do all this, but these are just ideas. Yep. Try them with different amounts of contamination, and then also we need to use it with a piece of some windings. We need to cut some windings and drop it in with it so that we can test to see, is the varnish coming off, is the plastic coming off.
Yep.
There's a lot of unknowns. We can't test every possible aspect, but these are other factors that we can add in to see what does happen.
Well, and we can get really close to real world scenarios and conditions that might explain what you're seeing in the field. Not only when you cut open a compressor, but when you dump a compressor out. Why is it the color it is? What does this mean? What does that mean? How did we find this? Because there's a lot of things that we say in the field that have no real physical science back behind the explanation. And so, I've heard it many, many times where the color of the oil in the system is because they didn't braze with nitrogen. Well, how do you know that, right?
Yeah.
And so that almost makes me want to, well, now I have another idea, right? Taking a piece of copper that we braze without nitrogen and then flushing it with oil and then cooking that oil and see what actually happens.
Right.
There's a lot of different things. What is the difference between what cupric oxide looks like in oil under a microscope as opposed to actual cooked oil, right? Because I'm sure there's a difference. And so these are all things that we're going to start exploring with these videos to just get down to the bare bones basic science of it. So
excellent. I look forward to it. I'm excited.
I'm excited too, man.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.